To round out the discussion on derivative shortcuts, I wanted to remind everybody of why we even talk about derivatives in the first place. Derivatives from a graphical sense are going to give you the slope of a tangent line. What I wanted to introduce today is the concept of a normal line. So in two dimensions, a normal line to a graph or to a function y equals f of x at x equals a is the line that is perpendicular to the tangent line at x equals a. So in the event that we have some sort of curve within the Cartesian plane like this, suppose that we wanted to isolate a value like this one right here. We'll say that this ordered pair is the ordered pair a comma f of a, and that this function is y equals f of x. If I were interested in the tangent line would touch the curve right at this point, but not actually pass through it. And the slope of this tangent line would be equal to f prime of a. You take a derivative, we plug in the x value that was given to us, and that's that. A normal line is a line that is going to be perpendicular to this line. So for the slope of a normal line, I'm going to ask you to go all the way back to your old algebra classes and say, what is the relationship between two lines that are perpendicular in terms of their slopes? And that would be that they are opposite reciprocals of each other. You'll notice that as this one is drawn, the slope of the tangent line appears to be negative and the slope of the normal line appears to be positive. They will always have opposing signs, but additionally they'll also be reciprocals of each other. So to give you an idea of what something like this could look like, let's consider f of x is equal to something relatively straightforward, like x squared minus 3x plus 7. Let's find the normal and the tangent line. So we'll find the tangent line and the normal line at x equals 3. So tangent line and normal line at x equals 3. So in order for us to find the equation of a line, we are going to need both a point as well as a slope. Right now we only have an x value. We can turn that into a point by plugging it into the given function. So f of 3 is going to be equal to 3 squared minus 3 times 3 plus 7. First two terms will cancel each other out, and we will be dealing with a y value of 7 at our point. Now for both the normal line as well as the tangent line, we're going to need to take a derivative. Using our shortcuts for derivatives now, the derivative of x squared according to the power rule would be 2x. The derivative of minus 3x would be minus 3, and the derivative of plus 7 would be 0. So our derivative is going to be 2x minus 3. So for the slope of the tangent line, I'm simply going to plug in x equals 3 to the derivative. Now when we plug this in, this will be 2 times 3 minus 3 as we plug it into this expression, and we get 3. The slope of the normal line is going to be the opposite reciprocal of that. So negative 1 over f prime of 3. So that would be negative 1/3. So for the tangent line, we can go straight back to the point slope form of line and say y minus the y coordinate of the point, which is 7, is equal to the slope of the tangent line, which is 3, times x minus the x coordinate of the point, which is 3. Now if you wanted to be super fancy about this and put it into slope-intercept form, you would distribute the 3 and add 7 to both sides. We would get 3x minus 9 plus 7, that would be minus 2. For the normal line, we would do the same thing, same y coordinate, Same x-coordinate, but we would have a different slope this time. And the slope that we're using for the normal line is this negative 1/3. Now, again, if you wanted to get fancy and put it into slope-intercept form, you could distribute the negative 1/3. This would become a +1. Adding 7 to both sides would give you a +8 over here. And the slope of the line is still negative 1/3. So that's the process for finding both the equation of a tangent line as well as a normal line at a given point.